Welcome to VFD 101. My name is Thomas Russell. I'm a Senior Application Engineer at ABB. I'll be presenting this video based on basic operations of variable frequency drives. Today's agenda will be VFD terminology, electrical fundamentals, why we use a VFD, how a VFD works, motor basics, selecting a VFD, and VFD enclosures and options. What is the bypass? Building automation systems basics, common VFD application questions. VFD terminology. ABB, acronyms beyond belief. There's your joke for today. VFD is a variable frequency drive, also known as adjustable speed drive, adjustable freak drive, so on and so forth. Sometimes it just gets called a box on a wall. Pulse width modulation is how we control a motor. DVDT is a change of voltage over a change of time. IGBT is an insulated gated bipolar transistor. SCCR is the common short circuit current ratings. KAIC is an interrupting capacity of an individual device. Nowadays we use SCCR. Full load amps is FLA. ABB is formerly known as Aceta Brown Bavaria. K is 1000. FBA is a field bus adapter. When we use our drives and we have a communication system that's not built into our drives, it's a field bus adapter you'd buy for that device. EMI is electromagnetic interference, RFI is radio frequency interference, and EMC is electromagnetic compatibility. IEEE is the Institute of Electrical and Electronic Engineers. UL is Underwriters Laboratory. CE is a European conformity. DC is direct current. AC is alternating current. ACH 580-01 is a basic drive and comes with multiple different package designs. PCR, PDR comes with circuit breakers and disconnects. VCR and VDR are vertical packages with bypass. BCR and BDR are what we call box style packages with bypass. Let's talk some electrical and fundamentals. What is voltage? Formal definition of voltage is a different electronic potential between 2 points, measured voltage in AC or DC. HVAC equivalent is the voltage may be taught as pressure. We need pressure to move water or air. Likewise, we need voltage to move electrons to make electricity. In the right-hand side, we're showing AC voltage, where the voltage crosses zero and changes, and a DC voltage is a voltage that's direct current above the point of zero. What voltages are available and most common in the US and Canada? Single phase, 120 volts AC, was it used in your house? And then there's 208 to 240 volt AC, that comes into your house too, single phase. Three phase is what we use in our drives. It's 208 volt, 230 volt, 240 volt, more common in older cities. 480 volt is most common, and 575 is most common in Canada, and some data centers and some older factories on the East Coast, especially by Niagara Falls. What is current? The formal definition of current is the rate at which charge is flowing. It's measured in amps. The HVAC equivalent in current is a current may be taught as a flow. Flow is telling us the rate and how much water or air is moving. Likewise, the current tells us how much electricity is flowing. So how many amps does a device draw? Let's look at a fully loaded 10 horsepower VFD three-phase. 14 amps for a 480 volt system. And a fully loaded 100 horsepower VFD at 480 volt system will draw 124 amps. As horsepower went up, the amount of current went up. What is power? The formal definition of power is the rate at which electricity energy is transferred. It's measured in watts. It's also measured in horsepower. Power is proportional to current times voltage. The HVAC equivalent would be saying like a 20 horsepower supply fan moves more air than a 10 horsepower supply fan because it's a larger horsepower. So it's important to understand power is a good reference and commonly used in HVAC, but when it comes to VFD selection, voltage and amps are very important too. Horsepower can be misleading. A 10 horsepower 900 RPM motor, which is a low RPM motor, draws more current than a 10 horsepower 1800 RPM motor. A 10 horsepower 208 volt motor draws more current than a 10 horsepower 240 volt motor, and a 20-year-old 10 horsepower motor draws more current than a modern premium efficiency motor. A 10 horsepower 785 RPM motor running at 1850 RPMs draws more current than the same motor running at 1785 RPM. So we can refer to the NEC table 430.250 for references of horsepower to current. Remember though, that table is designed for the standard motors. So if you have a low RPM motor or a high RPM motor, then suddenly that table, you have to do the adders to it. Why do we use a VFD? VFDs control flow. Why do we want to control flow? HVAC systems are designed for the worst case situations, the coldest in winter, the hottest and most humid days in summer, with the highest occupancy. All other times, the HVAC systems are oversized. By reducing capacity, energy is saved, occupants' comfort is improved, and additional benefits are less mechanical wear and tear on soft, through the soft acceleration. You don't hear belts screaming when you start across the line. It eliminates the inrush and current spikes, resulting in voltage sags. So when you start a large motor across the line, it has a tendency to pull down your voltage from your transformer and causes issues that way. How do VFDs save energy? We are going to look at a fan or a pump curve. In this example, we're going to talk through this as a pump curve. The pump curve is graphed here, has to do with the amount of pressure versus the flow in gallons per minute. Pressure is on the y-axis, flow is on the x-axis. We have something called a control curve. The control curve is set depending on the speed of the pump. Where the control curve meets the pump curve, that's the operation point. In this case here, when the pump's running across the line, it will meet the control curve at 1,500 gallons per minute. And that requires a pressure of 40 feet of water. And there's your operation point. So let's look at power. Power is equal to pressure times flow. We have our operation point at full speed across the line. Our pressure is shown on the y-axis, and our flow is on the x-axis. The total amount of energy being used is power. That's pressure times flow. Now, the traditional methods of adding a flow restriction valve, what we see here is a pump, and there's a flow restriction valve. Let's say we want to change our flow from 1,500 down to 1,000. So to reduce the flow, we close the valve restricting the flow. This restricts the flow from 1,500 gallons per minute down to 1,000 gallons per minute. By doing this, we follow the pump curve. Now the pump curve is in blue, and because we just restricted the flow and the pump is running at full speed, what we have now is a total amount of energy. As you see here, this required energy is actually a little bit less than we had before, but it's still a lot of energy being used because the motor is still running at full horsepower. Now, when we add a VFD to the system, we have the ability to change the speed of the pump. We don't need extra valves to restrict the flow. So at this point here, let's take a look. By changing the speed of the pump, a new pump curve is created. The pump curve is in blue. We want to reduce our flow from 1,500 down to 1,000 gallons per minute. By creating a new pump curve by slowing the pump down, shown in green, we reduce the total amount of energy tremendously. The new pump curve meets the control curve at 20 pounds of pressure instead of 40. The energy required is much less than running the pump at full speed, saving you energy. Now, when we look at centrifugal fans and pump affinity laws, cubic feet per minute is directly proportional to speed. Static pressure is proportional to speed squared. And torque is proportional to speed squared. And horsepower, though, is proportional to speed cubed. These are the affinity laws. Let's take a look at it as a graph. CFM and speed flows very linearly with speed. Therefore, the faster you speed up, the more CFM you get. As you slow down, the less you get. But your torque, or your static pressure, is speed squared. Now, the big part is power is speed to the cube. Power requirements varies as the cube of speed. So let's take a look at what happens when I go from 60 Hertz down to 30 Hertz in the output of the drive. At 30 Hertz, I drop down and my CFM dropped down to half. My flow is only half the amount that I had at full speed. But the amazing part is the amount of energy I'm using, which is power, has dropped down to 12.5%. So a reduction of half speed gives you a reduction down to 12.5%, or 1/8 of the amount of power you need. This is how you save money. This is what makes drives so important in the HVAC business and many, many other businesses in the world. How does a VFD work? Let's take a look at what happens inside of VFD as a basic function. We'll come in with 460 volts, 60 Hertz, and we have a rectifier, which normally as a basic drive would be a diode bridge. That is converted to a 650 volt DC bus. Now that DC bus allows the IGBTs to convert a new voltage and a new frequency to control the motor. It's very important to realize we need to create a new voltage and frequency. Let's take a look at the input conversion part of the diode rectifier on a drive. We have our input voltage of 460 volts RMS. When you look at it though here in the chart, you can see around 650 volts is the peak. RMS is the root mean squared, and the peak voltage is around 650 volts. So, by going through the diode bridge, we end up rectifying the AC voltage. Now, if this cap bank was actually a resistive bank, we would expect to follow as voltage going up, you'd expect current to go up. But this is a capacitor bank. What happens though with the cap bank is that it gets charged up to a DC bus voltage. If there's nothing going out of the system, the DC bus voltage would equal the peak voltage totally and nothing would flow. No current would flow, it'd just be a static system. But as you run the motor, the DC bus voltage gets pulled down. In this case here, as the capacitor's voltage drops below 650 volts, every time the capacitor's voltage is lower than the peak voltage coming in through the rectifier, we see a current draw. And this current draw occurs as peaks. These peaks are what we call loads that draw current in this way are nonlinear loads. So as a nonlinear load, our current is only drawn whenever our DC bus voltage has dropped below the peak voltage of the incoming voltage. This is important because this is what causes nonlinear loads and causes harmonics. Now let's look at the output of the VFD. The output inverter has IGBTs. The DC bus is being charged by the input bridge. Now we're going to look at the output to the motor. Each IGBT is a high-speed switch. The high-speed switch can turn on or off to the actual capacitor bank in a positive or negative way. So let's look at one phase. We have a positive DC bus. The high-speed switch turns on. The voltage applied to the output of the drive on that phase goes to full DC bus voltage. When the switch turns off, we go back to zero. When the switch turns down to the negative side, we get a negative voltage. When the switch turns off, we're back to zero. Now this wouldn't be much of any help, but let's talk about what pulse width modulation is. Now, looking at the output, we have our DC bus with a positive and negative side, and we're going to turn on and off using the IGBTs. As we turn on and off, what's happening is we will stay on longer. To do this, we're creating more voltage to the motor. And by how often we do this, from positive to negative, we create a new frequency. So we do our pulse width modulation on the positive side, and we do it on the negative side, and what we have now is a new voltage and frequency for the motor. We do this in each phase. So how often you switch from positive pulses to negative pulses determines the voltage and frequency of the waveform. So we have our frequency, that's based on the x-axis, and our voltage is on the y-axis. Now a frequency of 30 Hz is half the frequency of 60 Hz. Now remember, when I say 30 Hz or 60 Hz, 60 Hz is 60 cycles per second, 30 Hz is 30 cycles per second. When we look at a motor and a drive, the output frequency and the amplitude of the voltage is needed to control the motor speed. So a higher frequency with a higher voltage has a higher speed on the motor. A lower frequency and a lower voltage gives you a lower speed on the motor. Looking at the fact we're doing this for 3 phases, we're changing the phases of each motor. As we look at the system, we're rebuilding a 3-phase output to the motor. Let's talk about motors for a minute. So, what kind of motors does the ABB 580 drive support? We control 3-phase motors. Most single-phase motors are not designed for speed control. VFDs control the frequency and the voltage applied to the motor, resulting in control of motor speed. ACH 580 types of motors supported are induction motors, permanent magnet motors, synchronous reductance motors, and Farad-assisted synchronous reducance motors. Look at the different types of motors we support. An asynchronous motor is an induction motor. It's the most widely used motor type. Permanent magnet motors are servo-type motors with strong built-in magnets. A synchronous reductance motor. Torque is produced through something called saliency. It's characterized by saturation. The flux gaps direct the flow of current in the rotor. So by having these open gaps in the rotor that are air, the current causes rotation. Synchronous reductance ferrite-assisted motors, a sync RM2. Torque is produced through saliency, just like the synchronous reductance motor, but the synchronous reductance squared adds a ferrites to the rotor to increase the torque generated and the field strength. So let's review quickly an induction motor. Its benefits are familiar. It's a proven technology. It starts with direct across the line. It's easy to use and maintain. It's one of the most common motors out there. Its limitations are its speed and accuracy is difficult without sensors, slip loss in the rotor, there's I2Rs that add the heat to the motor bearings, there's a lower efficiency and a lower speeds, especially partial loads. It drives less efficient at lower loads due to no load current. A permanent magnet motor is a very high efficiency motor, it has an IEC 5 or better, high torque density, excellent torque to inertia ratio, excellent partial load efficiencies, and a low noise level. Unfortunately, its rare earth magnets have high cost and limited availability. It's difficult to service because of high magnetic strength, and high EMF is a safety concern. These permanent magnet motors will produce high electromagnetic fields that can be actually high voltage that can hurt you. The required VFDs in order to operate them for most large permanent magnet motors. A synchronous reductance motor, a ferrite-assisted one, has high efficiencies, IEC 5 or much better than a permanent magnet motor. It has a synchronous speed, which means there's no slip. So if it's going at 1800 RPMs, it's 1800 RPMs. Its sustainable ferrite material is low cost, and we can get it pretty much anywhere in the world. It has low bearing temperatures and low winding temperatures. It has an excellent power density and lower current draw required for smaller power converters. It maintains efficiency at low speeds and partial loads. The limitation is that it requires a VFD to operate. You cannot put a permanent magnet motor, a larger permanent magnet motor for three-phase that we use on drives, or a synchronous reductance motor across the line. Let's talk about selecting a VFD. Let's take a look at how to size and select a VFD. What's the enclosure rating you need? It depends on where it's being mounted and what the mount environment is like. If it's mounted indoors in a non-dusty environment, a Type 1 is definitely needed. If you're looking at outdoors, you'll need a 3R minimum. What's the size of the motor? Look at the horsepower, the amps, and the voltage. Remember though, a VFD, when it comes to service factor, is a 1. On a motor's nameplate, you might see a service factor of 1.15. What does service factor mean? Well, a service factor means of a 1.15 on a 5 horsepower motor, as the nameplate shows here, is that you could run this motor at 7.5 horsepower on a 7.5 horsepower load. By doing that, though, the expected life expectancy of the motor will drop down dramatically, and the motor will run much hotter. When a motor is being ran by a VFD, we always consider the service factor of 1. Because the VFD's pulse width modulation that we talked about earlier actually causes more heat inside the motor. Therefore, you cannot run it beyond its service factor of 1. What's the facility voltage? You need to know that, because if it's a 460 volt system and you sell in 230 volt drives, you're not that bad off. You have the wrong drive. It won't support the 460 volt motor, but it won't blow up when you power it up. But if you sell a 230 volt drive into a 460 volt system, when you apply the 460 volts to a 230 volt drive, there's an issue. What type of options do I need? A disconnect type, bypass, harmonic diminution issues, and communications. There are all possible options you can buy with your drive. So some questions we can ask. What options do you need? Disconnect means, bypass, drive service switch, soft starters, which is a soft ramp to eliminate inrush, ultra harmonic drives, filters, input filters and other mitigation techniques to reduce harmonics, output filters for long cable lengths, option cards for communication protocols, and extra relay outputs. A UL Type 1. First of all, a UL rating is a tested rating. A NEMA rating is something that a company can just self-certify to. So if I'm working out of a garage and I say I'm a NEMA Type 1, it's because I believe that I follow the NEMA regulations and I've never tested it. I believe I'm fine. A UL Type 1 rating means that UL has inspected it. There's your difference between UL and NEMA. So let's talk about a UL Type 1, which is the same as a NEMA Type 1, but we're going to talk about ULs. ADD drives are UL rated. A UL Type 1 is for indoor use, and it provides a degree of protection against access to hazardous parts, and to provide a degree of protection of the equipment inside the enclosure against the ingress of solid and foreign objects. Basically, a UL Type 1 enclosure, the atmosphere inside is equal to the atmosphere outside. It's for indoor use. It's finger safe. So if you take your fingers and put your fingers up against the vents on the enclosure, you won't actually electrocute yourself. It doesn't stop a person from getting a paper clip and shoving it in there and finding out where power is, but it's designed to be finger safe. This is like almost every device in your house. It's a Type 1 device. It's for fairly clean and dry environments, and most mechanical rooms are Type 1. And it's the most commonly used enclosure for VFDs and a lot of other things. Let's take a look at the Type 12 enclosure. The enclosure is constructed for indoor use and provides a degree of protection against ingress of solid, foreign objects, falling dirt, circulating dust, lint, and fibers, and then there's filings. And yes, it's called filings. It provides a degree of protection against harmful effects of equipment and ingress of water, dripping or light splashing, and is giving you protection against the seepage of oil and non-corrosive coolants. Why do we have a Type 12 enclosure? This is based off the older style machine shops. When you'd have lathes that would be running to cut metal, it also used oil in order to have the cutting occur. This would cause filings, which actually are metal filings that are super, super small. They get attached to the oil and move up in the air and move around inside the room. Now, that's why you have your oils and non-corrosive coolants. So, looking at a Type 12 enclosure, we have ambient air on the outside is not equal to the ambient air inside the enclosure. We've upgraded from Type 1 to Type 12 when it's dirty, dusty environments. Construction phases versus normal phases is something to consider, but one of the things that happens is if you're going to have drives mounted in a mechanical room, especially in the desert areas where they open the doors up for cooling, that means you have a lot of dust and other things that could come in from the desert areas. So there's a limited chance for small amounts of dripping water, and you have to look at it, do I really want to put the drive there in the first place? ABB has a Type 12 enclosure system for the base drive that's very cost effective. A Type 3R and 3X enclosure is designed for indoor or outdoor use. It gives you a degree of protection against personnel and falling dirt. It also protects you against the ingress of water, rain, sleet, or snow, and that will be undamaged by external formation of ice on the enclosure. This does not mean you can wash it down with a garden hose. It's just for rain, sleet, or snow. The ambient air on the outside is not equivalent to the ambient air on the inside of the enclosure, but although air does transfer from the outside to the inside of the enclosure, we use things like enclosure heaters to prevent condensation building up. It's the most commonly used enclosure for outdoor VFDs. You can upgrade it to a 3RX, and we'll give you a stainless steel enclosure as required when you upgrade to 3RX. Remember, a 3RX adds increased protection from corrosion on the enclosure itself. Because the ambient air does transfer from the inside and the outside, or outside to the inside, the 3RX does not protect the inside devices from things like chlorine. Looking at a Type 4 or 4X enclosure, the enclosures are constructed for either indoor or outdoor as before. They will protect you against the ingress of solid foreign objects, falling dirt, wind-blown dust, personnel, but their advantages is the ingress of water, rain, sleet, snow, splashing water, or hose-directed water, and will be undamaged by the formation of ice. The ambient air on the outside is not equal to the ambient air inside the enclosure. You can upgrade to Type 4 and 4X when the VFD environment is extreme temperatures. Not all Type 4 or Type 4X designs are for outdoor use. Sometimes they're only for indoor use. It depends if they're designed for sun loading. The real question you have to ask yourself is, do you want to put the VFD where the location is that you require a 4 or 4X enclosure? Now, when we do a 4 to 4X, we add increased protection from corrosion. In this case, we use stainless steel enclosures and stainless steel air conditioners. The air conditioner is used to transfer the heat from inside the enclosure to the outside of the enclosure. If you were mounting this in a swimming pool area, outside would have chlorine, but the inside would not be affected by chlorine. So a stainless steel enclosure would be an applicable use for ice swimming pool areas and areas where you have gases like chlorine. So let's talk about what a bypass is. So there's something called a bypass. When you buy a drive, you can buy it with a bypass. What you need to know is the bypass allows the motor to run in bypass instead of the VFD, and it runs directly from utility power. The motor runs across the line at a fixed speed, and the motor starts with a high current draw. just like a normal starter would. So the bypass is there in case something happens to the drive. And what we call a classic bypass is a scenario where you have single phase issues affect the drive and the bypass. If there's a contact failure, there's nothing to protect that. There's no intelligence, there's no proof of flow. And if it's an auto transfer, let's say the drive trips out on a short of the motor, suddenly you transfer to bypass, there's no protection to that kind of stuff. That's what we call a classic bypass. For ABB, we sell the option of an Eclipse bypass. An Eclipse bypass provides intelligence. It has single phase protection. It has bypass protection to prevent the drive from transferring the bypass when it shouldn't drive through the bypass. It deals with the drive's operations. It has brownout protection. It allows the drive to continue running through a brownout, keeps the contactors closed, does a lot of things for you. There's no contactor chatter during a brownout. It has intelligence, so it has pass-through I/O. So what's pass-through I/O? The drive and the bypass have these abilities that if you have a communication system, and let's say you're not using a digital input or an analog input, you can send information to those inputs and pass it up through your building management system. That's what pass-through I/O is. It has welded contactor detection and serial communications that are built right into the bypass. So if the drive fails in bypass mode, you still can communicate with your system. And proof of flow. It can tell you in the bypass mode if the motor is actually spinning. It has safe auto transfer. Let's say there's a short in the motor, the drive trips out in a short, it's not going to transfer to bypass, so it doesn't blow your upstream fuses and circuit protection because it knows the motor can't run. It's got a short circuit scenario. Building automation system basics. What I need to know about. What does a building automation system provide? Energy savings, intelligence, and troubleshooting. So the amount of things your building automation system provides to the building. How does the BAS communicate with VFDs? The old way is through analog singles and contact closures. A start-stop signal, speed control and safeties and run stops and fault status and so on and so forth were all sent through the building automation to direct inputs, and that was it. The new way is serial communications. They're combined with analog contact closures depending on your systems. Some systems are pure serial communications only. The serial communications tells the drive when to start, stop, run, gives the drives all its permissives, and does the ability to program drive remotely and everything else. So when we look at serial communications, it's ones and zeros going across the wire. RS-485 is an electrical specification for hardwire requirements. It's not a protocol, it's just a specification for hardwire requirements. Common HVAC communications include BACnet, N2, Modbus, and LAN. So what's the buildings into the VFD, aka native? The analogy is RS-485 tells us communication verbally, like we're talking to right now. I'm verbally talking to you. But the communication protocol tells us how to talk to each other, like English, or Chinese, or Spanish. So RS-485 is just basically, this is the hardware communications way to wire it. But what it comes down to is your communication protocol is how you talk to the individual devices. When it comes down to the ACH 580, we have 119 points in the ACH 580 for BACnet that are native, that are set up already. You also can use certain abilities to get every other point in the drive if you need to. There's 55 points on the Eclipse bypass via VACnet. The common points are start, stop, control or monitoring, speeds, controls or monitoring, power, monitoring for lead credits and other rebates, and handoff auto status. For troubleshooting, you have fault codes, safeties, fault resetability, and for pass-through I/O, anything you want. You can pass it through from the drive or the bypass and send it up to your communication system as needed. So here's some frequently asked questions that we deal with when it comes to VFDs. A very common asked question is how many motors can I connect to one VFD? And the answer is, in theory, there's no limit. But you need to look at the motors being controlled by the VFD. In this case here, we're showing 4 motors here. They're coming down to individual motor protection devices, and then we're showing 2 VFDs as a redundant drive package. But one VFD would be turned on. It would be controlling all 4 motors at the same time. When we look at this, we ask ourselves, what do we need? If all the motors you want turned on and off by the VFD at the same time, this is a fine setup. All the motors being controlled run at the same time at the same speed. You need individual motor protection devices for each motor, or you have to have individual VFDs for each motor. That protection device can be located by the VFD or located over by the motors. How to size the VFD in this status? The size is based on the drive combination motors, full load amps, and horsepower. So you take all the motors, calculate out the full load amps by totaling them all up, and take all the motors' horsepowers and total them all up. And you size the ACH 580 for the horsepower and the full load amps. How far can I mount a motor from a VFD? There's two parts to this. Will the VFD be damaged or will the motor be damaged? You can go into the manual and you can go for the ACH 580 by frame size and determine what distance the drive can support a motor without the drive being damaged. But you need to go to the motor's information to determine how far the motor can be away from a drive. So that's two parts that you need to know of, not just the drive information, the motor information. Other things you need to consider is if you're doing multiple motors, what's your distance? If you have multiple motors and the MMPs are located with the drive and the motors are 50 feet away and there's 4 motors, that's 50 feet times 4, which is 200 feet. If you run one-way cable over to the motors for 50 feet, then have 10 feet per motor, then you're at 50 feet plus 40 feet, which is only 90 feet. So you have to look at what it is. And what's the fix? If you have a scenario where the motor's far away from the drive and you need to add something to it, you have to determine what solution you're going to have. Output DVT filters, sine wave filters, and items like that can be added to the output of a drive. They all cost more money. It's one of the things you have to look at by individual scenarios. Can a VFD have a single phase input? Yes, it can. We do have single phase inputs for VFDs, and we have outputs for 3-phase motors. We do not support single phase motors. So you can come in with 230 volt single phase into the drive, but you're going to go out and support a 230 volt 3-phase motor. Now be careful. People will suddenly ask you, saying, I have a 3-phase 230 volt air handling unit. I want to use your drive to support the whole air handling unit. The first thing you need to ask is, do you mean the motor and air handling unit, or do you mean the whole entire air handling unit? The drive is not a power conversion device. You do not want to plug it into a full air handling unit. You'll have many other issues. The ACH 580 can accept a single phase input and output 3-phase to a motor. See the user manual for VFD size ratings, and it must be doubled or more depending on the drive size. For the 580, you need to look at the user's manual to determine what size drive you need to support your motor. Certain ABB micro drives can accept like 120 volt single phase input, and they can output 240 volt 3-phase, but they're very limited to small size motors. We cannot single phase a system with bypass. The last thing you want to do is try to put a 3-phase motor across a single phase bypass. It will not be good and the results will not work out. This concludes this training video brought to you by ABB.